James has them, and today we're going to learn about electricity, because I said so. So look at, we got, how does electricity work? Well, opposites attract. So in a substance, in a material, we've got positive charges called ions, and we've got negative charges called electrons. Now, in some material, the stuff is fixed, but in some material, it can flow. So the negative stuff can flow and it can try to get to the positive stuff. And so if we've got a material where the positive is concentrated on one side and the negatives on the other side, we end up with an electric field. But if we have a conductor, so something that has electrons that can move easily, then current, the negative, can flow to the positive. So an electric charge, we can measure charge in a unit that's called coulomb. And the unit for that, the symbol for that is Q. So 1 coulomb is a massive number. It's 6.24 times 10 to the power of 18 electrons. So it's massive. But we need that because electrons are super tiny, so we never have just one electron. Now, the symbol for current is I, and it's measured in amps. So current, the number of electrons flowing per second is our current. That's how we measure it. So if we've got 10 coulombs worth of charge coming through a pipe every 2 seconds, then that means we've got 5 coulombs per second, or 5 amps. So an amp is a coulomb per second. And we use coulomb again because electrons are tiny. So otherwise we'd have a huge number here. We wouldn't be able to do. So now, everything I told you was a lie. Because what we said was that electricity goes from the negative side to the positive side, but actually, now that we think about it, it actually goes from the positive side to the negative side. We call that electron flow. Oh, sorry, it goes from the negative side to the positive side. So yeah, this is wrong now. This is what people used to think. The electrons are what's moving, so they move from the negative to the positive. And so the difference in charge between two spots is our voltage. It's also known as our potential difference, or potential. Now, when we have a system where there's a difference in charge, then the electrons will be attracted to the other side and they'll want to flow, and eventually they'll balance out. So we'll have an equal amount of positive and negative on each side, and then when we do, the flow stops because there's no more attraction. But if we had a way to keep the voltage difference steady, we would have flow forever, and we call that force electromotive force, or EMF. So here's a basic electric circuit. We have a voltage source, so power source, with a positive and a negative side, and then we've got a flow of current through a conductor, and we've got a load. So the load is what uses the power. If we didn't have a load, then we just have a short circuit, and that would be bad. So now, remember, electromotive force can come from 6 different methods at least. So we talked about these, but We got the magnetic field, which is super important because it's where most of our electricity comes from. And then we've also got chemicals, friction. So friction, when you rub two things together, you get static electricity. We've got heat, pressure, and light, so from solar cells. So here we have a circuit, so represented, so we've got a voltage source or electromotive force, and we've got 120 volts across it, and now we've got two items, two loads. So the voltage drops across the load, so it starts at 120, and then we lose 40, and then we lose 80, and we come back to the positive side, and it's 0. Because remember, electrons want to flow from the negative side to the positive side, and since there's a force, that means there's a difference of 120 volts across this system. So in order for there to be a difference, that means there's 120 volts here, and that means there's 0 volts here. So when the electrons move across, they lose some of that potential energy here, because this load has resistance. So yeah, we burn some of that energy, and then we come back, we burn some more energy, and we get back to 0, technically. So here's a complicated circuit, and what we see is the negative and the positive, and we've got, remember again, 120 volts. Now I've got 4 loads here, so we've marked these points as A, B, C, D, and E, and each one has a certain voltage drop. So we lose 20 volts here, and then 50 volts, and then 25 volts, and then 25 volts. So we end up at 0, which is okay. So you can see the difference between, any 2 points is whatever it's written here. So between A and B, we've lost 20 volts. Between B and C, 50, and then so on. So these little squiggly lines, zigzags, are resistors. Everything's a resistor. And resistance is measured in ohms, and it's the opposition that the material has to current flow. Because when electrons get into a load, they give that load some of their energy. So for example, if I've got a light bulb, that's a bad light bulb, but if I've got a wire here and I got the light bulb, what happens is my electrons are flowing down the wire, and when they get to the light bulb, there's some resistance, and they donate their energy. They get stuck here, and they donate their energy to the light bulb, and the energy from the electron gets converted into light energy, and we light up the room, but we lose energy, and so we experience a voltage drop across. And eventually, if we've got a lot of light bulbs, we end up with 0 volts at the end, whatever we start with. So copper, silver, gold, they're really good conductors. Glass, rubber, and plastic are poor conductors. But so we don't use them in electric circuits. Now I keep saying that, but V equals IR, and if we rearrange that equation, we get I equals VR. So current equals voltage divided by resistance. So you can write that down. Current equals voltage divided by resistance. We call that Ohm's law. So we want to know the current in this figure. We got 120 volts, and we got one load of 40 ohms, So what's the current? So remember, V equals I R. We can rewrite that so I equals V over R, or in other words, 120 volts, right, over 40 ohms gives us 3 amps, which is also known as 3 coulombs per second. That's the last time you will see that. So I here is 3 amps. Now here's another one. We want to know the electromotive force, aka the voltage. So with this circuit, we know we've got 2 amps and we've got 30 ohms. So V equals I R, which is equal to 2 amps times 30 ohms of resistance, which is equal to 60 volts. So, any questions, please post a comment. Thank you.